morning, chemists. How are you? Um, Isabel, good morning. Isabel, maybe log off, log back in. Hi everyone. So we have our paper due on Friday. So hopefully you were working on that over the weekend. So you can submit that on Friday. And then looking at the schedule, our exam's coming up in 2 weeks. So hopefully you are already preparing, right? Just the first day that you start hearing that information, start preparing for the exam. Don't leave it for the night before. But yeah, so that's basically all of our announcements. Let's do prayer and then let's jump into chapter 14, and then we'll probably finish 14 and start 15 today. All right, let's pray. Dear God, thank you for this week. Thank you that you've brought us this far into, the halfway point of the semester. I thank you that your grace is sufficient to carry us through the rest of the semester. So I pray for endurance and strength and for rest today in the midst of, I know people are feeling tired from the time change, but I pray that you would help everyone feel rested and ready for the day ahead. Bless us this week as we learn more about different reactions, different functional groups, but also as we learn more about who you are and your intelligent design and your love for us, Lord. I thank you for who you are. We praise you. We pray this in Jesus' name. Amen. All right, so we are in our learning checks. So here's the learning check. So our learning checks we were just looking at, we were talking about what's electron poor, what's electron rich, right? Electron poor, electron rich diene and dienophile. What reaction is that for? That's for the Diels-Alder. So remember that this week's lab is the Diels-Alder reaction. So you're going to be doing a Diels-Alder in lab. Make sure you're paying attention to what we've discussed in class as you're writing up your pre-lab and not just going about it blindly. Everything connects. These weeks connect with each other, what we're doing in class, what we're doing in lab, so that you can learn something. All right, so for our starting material for the Diels-Alder, we know this is the Diels-Alder because we have two different pi systems. Remember, this is called the 4+2 cycloaddition. And so with it being a 4+2, we can see we have 4 pi electrons in our diene and then 2 pi electrons in our dienophile. 4+2. So for this reaction, in order for the reaction to occur, our diene has to be S-cis. And so this is, in fact, S-cis with respect to the single bond, right? The two double bonds are cis one another, but we know that that's not the most stable conformation. So to draw this S-trans, we keep those bonds where they are, but we just rotate around. So we rotate around this bond, really. And as we rotate around that bond, our other alkene ends up on the other side, where the double bond is still in the same conformation. So the whole thing is an S-cis diene, but for this alkene, it is trans. And the same for this alkene, it is trans. And so it still needs to be trans and trans, as the whole diene is S-trans. So I'm showing you that this is what it would have been to begin with. To begin with, it would have been S-trans because this is more stable. But it has to rotate around from S-trans to S-cis in order for the reaction to occur. It must be S-cis for the Diels-Alder. And then we also had, so we know for our Diels-Alder, we have to have the S-cis diene. And then for our dienophile, we have our endo rule. And so for the endo rule, we know that we want to have as many groups in the endo position as possible. What's the endo position? Pointed toward the diene here. You can see that up here at the top. That's endo. And so it's not like we can change this transalkene to being cis. It cannot be changed to cis. We can't try to put both of these groups into the endo position. So we get as many groups as possible into the endo position. As many groups as possible into the endo position. Here, we can only have one group in the endo position. The other group has to remain in the exo position because this is a transalkene. We can't go from trans to cis alkenes, right? We can't change that. All right, so for our Diels-Alder reaction, we had to change from S-trans to S-cis, something higher in energy, and then we have our endo rule. And so then when we do this reaction, let me number these carbons. I'm going to number this in the same way whenever we do this reaction, because I want you to see that we're making this six-membered ring. And so when we do the Diels-Alder, here's our arrow. Let me do it I'll do it in green. From the middle of this bond to carbon 4, from the middle of the 3-4 bond into the 2-3 bond, and from the middle of the 1-2 bond to carbon 6. Or you could rotate, you could do those arrows going in the opposite direction. It would have been fine going the opposite direction as well. It just needs to be a cyclic movement of all these electrons. And so we end up always in a Diels-Alder reaction with a six-membered ring. We always end up with a six-membered ring. And so I'll number it the exact same way: 1, 2, 3, 4, 5, and 6. So what arrows did we draw? We drew an arrow making a bond between 5 and 4. We can see the 5-4 bond. We drew an arrow making a bond between 1 and 6. And then we drew an arrow making a double bond between 2 and 3. So we always get a cyclohexene. And with that, we can look at the stereochemistry here, up here at the top, to figure out the stereochemistry of our product. So anything that's in the endo position is going to end up on a dash. So on carbon 5, we have a double bond to oxygen. We have an oxygen, and we have a methyl. That's what that CO2CH3 is. It's an ester. But then on carbon 6, it's in the exo position. And so exo, we know that that's going to be a dash. And then on carbon 1, we have a methyl. Now, is this methyl inside or outside? Well, you have to remember that on carbon 1, we also have a hydrogen. And so the methyl is outside and the hydrogen is inside. We don't have to show the hydrogen that's inside, but we will show that the methyl is on a dash. And we're assuming that there is a hydrogen there. If we're not showing anything else on carbon 1, there's a hydrogen there and it's on a dash. I'm sorry, it's on a wedge. Same thing for carbon 4. This is outside because there's a hydrogen inside. And so we're going to do a dashed line. That is our product there. So we get this. It would have been just as likely for this reaction for us to have, if we had flipped it, for this to end up in the endo position and this to end up in the exo position. So it wouldn't have mattered if we had drawn the product that you see there or this product, where now the ester on the top is in the endo position and the ester on the bottom is in the exo position. Same difference here. These two are diastereomers. All right, questions on this one?
Doctor, so we can draw either one then, or do we have to draw both of them?
No, you can draw either one.
Okay.
So you just really need to follow this up here. All right, let's do another one with this. So again, 4 plus 2 cycloaddition. 4 pi electrons, 2 pi electrons. We have to heat it for the Diels-Alder, but we know we're doing the Diels-Alder reaction when we see it's a 4 plus 2. Looking at our starting material, we already have this in the S-cis position, conformation. So this is good for the Diels-Alder. It's good for the Diels-Alder because we don't have to waste energy moving it from S-trans to S-cis. It's set up as S-cis. Oh, actually, let's go back and do one more thing. I forgot to talk about electron-rich or electron-poor. So we can see here that for our diene, it is electron-rich because we have those alkenes pushing in electron density, and we can see for our dienophile, it's electron poor because of the esters. Those esters are with electron withdrawing groups by resonance. But the alkene is an electron donating group, just like what we just were talking about at the end of Friday. All right, so back to our example here. We know that this is an electron-rich diene because we have these groups here that are donating in electron density. And we know that we have an electron-poor dienophile because this is an electron withdrawing group by resonance, right? We can move electron density up into this bond and up to the oxygen. So that is going to give us a positive charge in one of those resonance forms. So we're good there with the conformation for our diene. S-cis is good. We're good because this is electron rich. We're good because this is electron poor. Now remember our endo rule. Is this following the endo rule? No, because the aldehyde there is in the exo position. So really we need to redraw this so that we have our aldehyde in the exo position. I'm sorry, the endo position. Now we're ready to do our Diels-Alder reaction. So when I number this, I'm going to number the 4 carbons of the diene and then the 2 carbons of the dienophile. I'm not going to number all the way around this 6-membered ring because all those carbons aren't reacting. What's reacting, so here I'll do my arrow in a different direction. Let's go here, so into the middle of this bond. From the middle of the 3-4 bond to carbon 5, and from the middle of the 5-6 bond to carbon 1. So that's the opposite direction to what we did last time. So in this heat, we're going to have, again, a 6-membered ring with a double bond. Carbon 1, carbon 2, 3, 4, 5, and 6. So we have our endo rule. So we moved our group on carbon 6 to mean endo. And so we know that on carbon 6, we're going to have the aldehyde, but we're going to have to show the stereochemistry. That's on the dash line. And then we have on carbon 4, what do we have? Inside or outside? On carbon 4, these are inside bonds because on carbon 4, we also have these hydrogens pointed outside. And so with these hydrogens pointed outside, I don't know if it'll let me draw it. Okay. So you know that should be on the end of the bond, obviously, but I just can't draw it down there without it trying to add subtitles. So pointed toward the inside, we have a dash line. But notice that this is a whole chain where 1 and 4 are connected to each other. So we're going to have carbon 1 bonded to carbon 4 with these 2 carbons in between. We can call them 7 and 8. Where now both of those have to be wedges. But not the bond in between 7 and 8. But the bond from 4 to 8 is a wedge, and the bond from 1 to 7 is a wedge, meaning that these are coming towards you and above. So another way to represent this, the same exact thing, would be like this. This didn't work. So we break the bond in the back. So notice that this bond is broken because we're kind of showing that these other bonds are in the front here. So this in the front would be, if I number this, this is carbon 4. Up top here, this is carbon 8. Over here, this is carbon 7. And over here in the back, this is carbon 1. And so we break the bond between 1 and 6, saying that, okay, this is in the back. We can't see this because we see the 4-8 bond in the front. The 1-6 bond, we can't see it as well, and so they break it. And then we have 2 and 3, and then we have 5. But what else should be bonded to 6? Well, on 6, we have pointed down, because we know up, we have a hydrogen. Pointed down, we have this aldehyde. 2 ways of showing the same thing. Which way is better? This way is better for you because this is going to end up looking like a mess. So it's better for you to do this one that I have on the bottom, where you just continue with, you have a 6-membered ring, and then if you have more, another ring above, so we have this bridge above, then we can just show that in the middle of that 6-membered ring. Questions on this? All right, then let's move on to another one. So we had our 4 plus 2 with the Diels-Alder. Now, if we have this system, now this isn't a 4 plus 2. Now this is an extended pi system. And so for an extended pi system, now we're talking about electrocyclic. All right, so we have an electrocyclic reaction. Let's look at how our arrows are going to move. So we move our arrows, and we can start either side, but we move our arrow here. I'll go from the middle of this bond, attacking this bond. I don't want to attack the methyl on the end, right? The methyl on the end of the chain, I can't attack that because there's nowhere for the electrons to go. But if I attack this carbon, I know that I can move electrons over into the middle of this bond. But then the carbon right beside it have too many electrons, so it can shift over its electrons. And we could do the same over here, where in the beginning, the first arrow that we had drawn, we had lost electron density, so this carbon would have had a lack of electron density. And so we move in that last arrow, bringing in that electron density needed for now all of these carbons to have a full octet. And so those are atoms, so we'll number it. Those are the atoms of the ring. So we're going to get an 8-membered ring. Where now we have a double bond here between 4 and 5, between 2 and 3, between 6 and 7, and then we made a single bond between 1 and 8. That's what those arrows told us. So as we look at this now, we are looking at 2 carbons that are being rehybridized. Which 2 carbons are being rehybridized? Can you put that in the chat? They're always in an electrocyclic reaction going to be 2 carbons that get rehybridized. Which 2 carbons are rehybridized? Yeah, 1 and 8. So we're looking at carbon 1. We're looking at carbon 8. As they get rehybridized, they go from being sp2 here to being sp3 over here. So we know we have methyls attached still, but we have to figure out, are those methyls going to be wedge or dash, right? sp2, that's where we think about inside, outside. sp3, though, that's where we think about wedge dash for our stereochemistry. So inside, outside, or we could say cis, trans, EZ for those double bonds. All right, so what are our fingers doing? So remember, for our fingers here, if we're doing inside, outside, this is sp2, this is trigonal planar, then we need to start off with our fingers, and everyone should be doing this. Our fingers should be flat, right? And we're going to be, with our fingers flat, moving them to straight up and down, right? But are we doing a conrotatory or disrotatory ring closure? Or we have to look at how many pairs of electrons are moving. We have 4 pairs of electrons, E, D, C. What is this? Light, photochemical. And so photochemical, remember light came first and then heat. So P, photochemical, T, thermal. So this is disrotatory. So disrotatory means that they're not both moving in the same direction, right? One's clockwise, one's counterclockwise. All right, so disrotatory, we start off flat. And where are our methyls? They're both pointed toward the outside on 1 and 8. Everyone should be doing this. 1 and 8 are on the outside. Disrotatory, as we do this, 1 and 8, methyls end up either up or down. If they're outside here, then you should see that they either both end up or down because this is disrotatory. If it was conrotatory, they'd both move in the same direction. One would end up, one would end up down. But for this, we could draw this product as a wedge or as a dash. It turns out that for this product, though, we have an internal mirror plane, and so this is meso. So if you draw it wedge or you draw it dash, it doesn't matter. Those are the exact same thing. We're not getting 2 mirror images. This is superimposable. So this is our product here. So technically here, you could just draw the methyls regular. No need for the wedge or the dash because this is a meso compound. It's achiral. Questions on this? All right, let's look at this. So again, we have an extended pi system. And with this extended pi system, we're going to be doing a ring opening. So from the middle of this bond over here, middle of this single bond, we can break a single bond to break open the ring. and then middle of this bond into the middle of this bond. Which two carbons get rehybridized in this? What do you think? Exactly. 1 and 6 get rehybridized because now carbon 1 and carbon 6 go from being sp3 to being sp2. So carbon 1, carbon 6, they're both sp3 here. Now they end up being sp2 in the course of this reaction. So let me number these. So looking at this, we have 3 electron pairs. So that's OCD, odd number. Photochemical. So we know that that is conrotatory. Always photochemical before thermal. So conrotatory, all right, let's look at our fingers. sp3, that's tetrahedral. That's our wedge dash. And then we're going to go to trigonal planar. Where we're talking about inside, outside, cis trans, EZ. All right, so we're starting off with straight up and down. Everyone should be doing this. Straight up and down with our fingers, right? What do we have on carbon 1? A methyl below. What do we have on carbon 6? A methyl above. So here are our methyls, and we're doing conrotatory. So if we go both clockwise or both counterclockwise, here we end up with outside, outside. Or if we go this direction, inside, inside. Can we do either one there? No, right? We can't rotate where we have one above, one below, where we end up rotating into the middle. We cannot make this product where we end up pushing these methyls into the middle, right? A lot of steric hindrance. So all we can do is have our methyls pointed toward the outside, hydrogens toward the inside. So that is our product there. Outside methyls, not inside methyls. Only one product possible. All right, let's look at this next one. So the same exact starting material. We'd have to do a ring opening, but look at this. Heat now. So what would the difference be for this? OCD, it would be disrotatory. So the same exact product, making a triene. But now, so one's above, one's below. One's above, one's below, disrotatory. So we can rotate both toward the inside, where now we have, so we had one above, one below. They end up here. Or we could go outside, where they end up both pointed toward the same direction, kind of. So we end up with this kind of a product. So we can do this pointed toward the outside and this pointed toward the inside, where they're kind of both pointed in the same kind of direction. But really, this does not form. Why does this not form? This really doesn't form because when we're looking at this, we have to remember that we are doing a ring opening of a 600 ring with heat. Really, no reaction here because this is not favorable to do this ring opening. It's not favorable to do a ring opening of a 600 ring thermally. A 4-membered ring, yeah, we can open that because a 4-membered ring is unstable. But we're taking something that is stable and taking it and making something less stable. And so just thermally, no, right? This is where we had something low energy and we're trying to make something higher in energy. This 600 ring being closed is more stable. So it doesn't matter what's on it. 600 ring is closed, which is more stable than making this triene. It's better for us to have it in a ring. And so thermally, there's too much energy here, right? And so we said we could take that exact same system, but we add in light. So then we can do the reaction. So that's why this one works with light, because it's this case where we have excited it up. We've gotten to an excited state where it's less energy needed. But if we're just talking about here, this is just thermal, this doesn't work. No reaction here, not favorable. Both of these methyls are pointed in the same direction, so they're both pointed in the same direction. It's just kind of hard to see with how I've drawn this, but both of the methyls are pointed toward the top. But it's just because of how I kind of curved this alkene up at the bottom. Then if it's curved up a little bit, then you can't really tell, but they're both pointed toward the same side. All right, questions on this? All right. So that's our Diels-Alder and our electrocyclic reactions. Here's one more thing we have to do. Looking at this, we need to redraw it in the S-cis. Why would we need to redraw it in the S-cis? Because this is required for the Diels-Alder. All right, so we looked at this kind of thing before. Let's number these carbons so we keep track of everything. All right, so what kind of double bond do we have? Well, we need to make sure that we maintain any of the stereochemistry in the alkenes themselves. So this is a cis alkene. This is also a cis alkene. But looking at the whole thing, using our single bond as the line of demarcation now, it's S trans. We want to make it S cis. So how do we do that? The easiest thing to do would be to leave one of your double bonds as is. And then with this, in order to make this S cis, through our single bond, we have to have our other alkene on the same side. We're rotating around. And so as we rotate around, we end up with, so here's 5, 4, 6, 3 and 2 now rotated onto the opposite side. The opposite side of that alkene. of the single bond. So what was the double bond between 2 and 3? It was cis, so it still needs to be cis. And so we end up here, where it's still a cis double bond. Here, look at what we have ended up with. We've ended up with carbon 1 and carbon 6 trying to occupy the same space, right? This is very sterically hindered. So this is going to have a slow reaction rate for the Diels-Alder. But we've drawn the whole thing in S-cis. Let's look at this next one. So again, this is S-trans. With respect to the single bond, those two double bonds are on opposite sides of the red line. What is the bond between 4 and 5? That is a cis alkene. Let's keep it cis. Then what we're doing now, again, is rotating around. And so as we rotate around, we end up with our 3-2 bond over on this side of the single bond. So now this is S-cis. So what was our double bond between 3 and 2? Well, both of our methyls were on the same side, but those wouldn't be the high priority group. So technically, this alkene would be E, right? Where carbon 1 is high priority and then carbon 4 is high priority. And so this would be an E alkene. So it needs to still be an E alkene. But those two methyls need to be on the same side as one another. So we know that in order for this to be E, carbon 1 has to be over here. Because with respect to the double bond between 2 and 3, we know carbon 4 and carbon 1 need to be opposite one another in order for this to be an E alkene. And so we have our carbon 4-3 bond. Now we have our 2-1 bond. So we know that this is still E. Here's our carbon 1. Now, where is this methyl? This methyl needs to be cis to our carbon 1, and so it ends up here. So this is our S-cis diene. Ready for doing the Diels-Alder reaction. Questions on that? All right, if we have no questions, then remember that your problem set will be due on Wednesday. And then we will start chapter 15 now. So in chapter 15, now we're going to begin discussing benzene. And so remember we said benzene has its own special reactivity. And so we're going to look at 2 whole chapters just devoted to benzene and the reactions that it can do. But first, let's look at Psalm 61. It says, "Oh God, listen to my cry, hear my prayer. From the ends of the earth, I cry to you for help when my heart is overwhelmed. Lead me to the towering rock of safety, for you are my safe refuge." So I know that a lot of you guys are feeling overwhelmed right now. Like it's a pretty difficult part of the semester. We're heading into a lot of assignments and exams, all kind of back to back, I know for all of your classes. So know that you can cry out to God and know that he will actually listen to you. He'll hear your prayers. But cry out to him. Know that he is your safe refuge. He is your rest. He will help you through all of this. All right, so looking at benzene, what did we say about benzene? We said benzene is cyclic, right? It's a ring, and it is a triene. We have 3 double bonds in it, which means that every benzene ring has 4 degrees of unsaturation, right? Rings and pi bonds. So 1 ring and 3 pi bonds. So it has 4 degrees of unsaturation. Remember, we also said that benzene is especially stable. It does not participate in alkene or triene reactions. It won't do those reactions that we discuss in chapters 11, 12, and 14. It's going to have its own special reactions. Remember, we also discussed that for benzene, we have these 2 resonance forms that are equal in stability. And so we can draw it with the double bonds or with a circle, but you have to do one or the other, because if you just do this, right, this is just a cyclohexane. We have to put the double bonds in it. I've also seen some people do double bonds like this. No. Double, single, double, single. It's conjugated. So make sure you are not just rushing and drawing your double bonds incorrectly. It always is double, single, double, single, double. So let's talk about how to name them. We call benzene and its derivatives aromatic. We call them aromatic compounds. So when something has a benzene ring, we say it's an aromatic ring. And this is because back in the day when these aromatic compounds were discovered, these benzene compounds, they all had a strong aroma. And so with that strong aroma, they called them aromatic compounds. So we'll talk about how aromatic actually means something else now. So how do we name them? Well, we know just a 1 benzene ring that would be called benzene. Add in 1 substituent. We put the name of the substituent, so fluorobenzene. No number needed. Nitrobenzene. What's a nitro group? This NO2. Notice that the bond is drawn to nitrogen, and the 2 oxygens are on the outside. A nitro group looks like this. Nitrogen, double bond to 1 oxygen, single bond to an oxygen, oxygen with 1 bond to it, negative charge, nitrogen with 4 bonds, positive charge. That is what the NO2 group looks like. So you need to make sure you're drawing your bond to the nitrogen, not to the oxygens. Then we have here 1, 2, so we know it's an ethyl with 2 methyls, so 1,1-dimethyl ethyl, benzene. No number needed because there's only 1 substituent coming off of this benzene ring. But we know this has a common name. The common name would be tert-butyl or T-butyl benzene. You know that T-butyl group. We have other common names when they are di-substituted. Di-substituted benzene rings have common names. We have the common names of ortho, meta, and para. So let's look at each of those. So for our first case we'll do meta first. So this is 1, 2, 3. So it's like a 1-3 arrangement of those 2 groups. And so this one is called meta, where notice that these bonds here kind of have an M shape to them. With the substituents, meta ends up looking kind of like an M. So that's one way to remember meta, but it's a 1-3 arrangement. And then we have para. So para, that's going to be 1-4. This is as far away from each other as they can get, because if I move one of these methyls over 1, it ends up being 1-3 in either direction. So this is as far away as these can get. And so for this one, think about a parachute. What do you want for your parachute? If you jump out of a plane, you want the walls, the sides of that parachute to be as far away from each other as possible, right? If the walls of the parachute are close together, you're falling straight to the ground. But if they're as far away from each other as possible, now you have this nice parachute, you fall nicely, lightly to the ground. That is the same with this. Para, it's 1-4, as far away from each other as they can be. If you move it over one way, either side, it's a 1-3 conformation. So para with 1-4 is as far away as they can be. And then our last one is just here, 1-2. This is ortho. So we have ortho, meta, and para. Ortho is just a 1-2. Then we have meta, which is 1-3. Para, which is 1-4. Or we can write O, M, or P. You can write out the whole thing, or you can just do O, M, or P. Again, this is only for disubstituted. Only for disubstituted. And it is a common name. So how do we do our IUPAC name? So IUPAC's up here, and then common is the next one. So for our IUPAC, we give everything the lowest number possible. So 1-2. So 1,2 dichlorobenzene. If we're talking about the common name, though, this is a 1-2 arrangement. So ortho dichlorobenzene. No number. If you say ortho, that means it's 1-2. So you don't have to say ortho 1-2. You just say ortho dichlorobenzene. That means these two chlorines are in a 1-2 arrangement. Here we have two substituents. How do we know which one's on carbon 1? Alphabetical order. Bromo versus nitro. To break that tie. Just like we were doing before with our rings, right? We've done this before. So 1 bromo, 3 nitrobenzene. Or meta, this is making an M. Meta bromo nitrobenzene. No dashes, just bromo nitrobenzene. Then our next case, we have ethyl. And we have here 2 carbons with a methyl, so 1 methyl ethyl. So this would be here a 1-4 arrangement. Ethyl would be on carbon 1. The methyl ethyl would be on carbon 4 based on alphabetical order. So 1 ethyl 4, 1 methyl ethyl, benzene. Then we have a common name that actually has 2 common names in it. Our common name is para. That's common. And then isopropyl, also a common name. Instead of methyl ethyl, we know that that group is an isopropyl group, but we said that that's common only. So para-ethyl isopropyl benzene, E, and then I for isopropyl. Let's just review here. When we have sec-butyl and tert-butyl, alphabetical order is B. But if we have isopropyl, it's I, or isobutyl, I. If you don't know what these are, make sure you review because that's stuff from last semester. Questions on this? All right, so orthometapara only applies when you have disubstituted benzene. So if you have tri-substituted or more highly substituted, so up to 6 different things attached to the benzene ring, right? Because each of those carbons can only make 1 bond. They all have a double bond and a single bond, so they only have 1 more bond they can make. It's either hydrogen or some kind of substituent. But if we have more substituents than just 3, now we don't have common names. We just can do IUPAC names. And so with this now, we have to give everything the lowest number possible. So here, for this first one, it's a 1, 2, 3, but which one is on carbon 1? is this methyl over here on carbon 1 or this bromo? Alphabetical order breaks the tie. So first give everything the lowest number possible, then alphabetical if there is a tie. Lowest number possible, then alphabetical to break the tie if there is one. There is one here, so 1 bromo, 2,3-dimethylbenzene. Here, our lowest numbering possible, 1, 2, 3, 4. We couldn't do 1, 2, 3, 4, 5, right? There's only one set of numbering that is possible. The only set of numbering that is possible here, because lowest numbering is what we care about first, would be 1, 2, 4. So 1, 2, 4 trinitrobenzene. Here we have our lowest set of numbers would be 1, 3, 5. Anything could be carbon 1. And the other things would be 3 and 5. So we break our tie with alphabetical order. So we have an ethenol versus ethyl versus ethynyl. And so those three things we have to put in alphabetical order. And so we number it from the ethene to the ethyl to the ethynyl, because then even with calling this carbon 1, we'd still have a tie with what's on carbon 3. And so we break that tie with alphabetical order also. So alphabetical breaks 2 ties. Question on that? All right. So here we have a lot of benzene derivatives. Many benzene derivatives are known by their common names. And we've seen a lot of these already in the lab. So here are the ones that you need to know. Know these common names. You need to know toluene, right? We've seen that in lab a few times. Xylene, another solvent. I believe we've seen xylene before. And styrene. What do you think styrene is used for? The production of styrofoam. We saw this in our polymer chapter. And then you also need to know phenol. We've seen phenols before. Aniline. And benzaldehyde and benzoic acid. For benzoic acid, it's a carboxylic acid, so they're drawing it in one way. Here's another way. We have our carboxylic acid. That's what that COOH means. CHO, that is how we abbreviate an aldehyde. I want to put it over here on this carbon. But that's what CHO means, carbonyl and then a hydrogen on it. So make sure you know these common names that I put the asterisk beside. But also for some of these common names, they are acceptable for IUPAC and common. These ones are going to be acceptable for IUPAC and common. They've been known for such a long time that we don't even call them by their IUPAC name. The ones that are acceptable for IUPAC and common are phenol, benzaldehyde, and benzoic acid. These are used in place of the systematic name. So we don't call anything benzenol or benzene carbaldehyde or benzene carboxylic acid. We just call it phenol, benzaldehyde, benzoic acid. But for a lot of these other things, even when we're talking about them, we don't say methylbenzene, right? In lab, I said, get the toluene, because we have just known these things for so long that a lot of them are just known by their common name. But the common name isn't acceptable if we're writing the systematic IUPAC name for many of these. But it is acceptable for phenol, benzaldehyde, and benzoic acid. Questions on these? So make sure you recognize, so our toluene has a methyl group, but xylene has 2 methyls. And those 2 methyls could be ortho, meta, or para to one another. Then we have styrene, where we have that ethenol group, right? We need that alkene to be used for the polymerization reaction. Our phenol ends with OL. We know that's an alcohol, phenol. Aniline is an amine. So NH2, nitrogen makes 3 bonds. So NH2. Then we have our aldehyde, benzaldehyde, and our carboxylic acid, benzoic acid. So make sure you can recognize these because they're going to be a part of bigger compounds. So here we have these compounds where there are 2 or more substituents, and we need to remember that some of these are common names from this previous slide. So here we have a methyl and we have an iodine, alphabetical order, 1, 2, so 1-iodo, 2-methylbenzene. But we have to recognize that for the common name, this is called toluene. And so if that's called toluene, then we say that we have an iodo group that is ortho to the methyl of toluene. So ortho-iodo-toluene, not ortho-iodo-methylbenzene. For the common name. Remember, the common name is in parentheses. Just that's how they show up. But you don't have to put the common name in parentheses when you're writing on the exam. All right, so then we have here this compound with an OH attached to the benzene ring. And so we know that that is called phenol, which is acceptable for IUPAC and common. So if it's acceptable for both, then we can put it into our IUPAC name, ending with phenol, and that has to be carbon 1. It has to be carbon 1. If the whole thing is named as a phenol, carbon 1 has to have the OH on it. So then this would be 2, 3, 4, 5, 3, 4, 5, 6. So 2, 4, 6 tribromophenol, and you could have numbered it obviously in the opposite direction, but this has to be carbon 1 because the whole thing is a phenol. Then our last one here, we have 1 bromo, 3 ethynyl, benzene for the IUPAC name. But the common name, we have styrene. And so with styrene there, what is it? Well, it's a meta disubstituted benzene ring, so meta-bromostyrene. Let's look at another one with these. Some of the common names, so they have further common names, refers to the aroma of the compound. Remember I said these are aromatic? So methyl salicylate, that's that wintergreen flavor. Vanillin is the name of this, the common name, vanilla flavoring. Thymol, that's the thyme flavor. But for these, let's look at how they're named. So for this, more bonds to oxygen, higher priority group. So here we have a carbon with 1 bond to oxygen versus a carbon with, this is going to be 3 bonds to oxygen. This is an ester. So what we have here, OCH3. 3 bonds to oxygen. So more bonds to oxygen, higher priority group. So we name the whole thing as a benzoate. And then this is a substituent, a hydroxy substituent. We don't name it as a phenol. The whole thing gets named as an ester. It's an ester, not a phenol. Because we only have 1 bond to oxygen. Here, 1 bond to oxygen. We know ethers are low priority anyway, but then this carbon, what is that? Aldehyde, which we know would be 2 bonds to oxygen. So that's a higher priority group, so we name the whole thing as benzaldehyde. Remember, benzaldehyde is acceptable for IUPAC in common. So the whole thing gets named as a benzaldehyde. So this has to be our carbon 1, 2, 3, 4. So it's 4-hydroxy, alphabetical order, 3-methoxy benzaldehyde, which is vanillin. Now, this is the only thing with a bond to oxygen. So the whole thing is named as a phenol now. That's our carbon 1, giving everything the lowest number possible. We number it around this direction. So 5-methyl 2, 1-methyl ethyl phenol. Questions on that? All right, we'll stop there. We'll pick this up again on Wednesday. Don't forget to work on your problem set with your group. Don't forget to work on your pre-lab where you think about it. You use your brain before you come to lab. All right, have a good day, you guys. I'll see you for office hours and I'll see you for class. Bye. Anybody have questions?
Volume, I have a question for the pre-lab. So we're skipping step 1, the cracking, right? And then we're going to.
Right.
So which ones in the lab manual or the book should we start with? Like step 2 or?
Look at the numbers for what it says for the lab, right? It says it's chapter whatever dash number. So so look at those numbers in the textbook and you only do the ones that beyond the cracking. Do you understand what I'm saying?
Yeah, so there's 3. Okay, got it.
So this is 48, 1, 2, 3. So I think 1 is the cracking. So you do 2 and 3.
Okay, got it.
Other questions? All right, you guys, have a good day. Bye.